In earlier videos, we had defined the torque, and we had seen that the angular acceleration is determined by is proportional to the torque acting on the system, where this is the angular inertia, angular acceleration, and this is the torque acting on this. And now we will be try to analyze the relation between the torque and alpha in more detail. What we will be aiming at is try to get a relation similar to, you see, this equation is similar to Newton's second law, which states that the force is proportional to acceleration, and the proportionality constant between the force and acceleration is the mass. So what replaces the mass in the case of rotational dynamics? To determine what that proportionality constant is, first let's study a very simple system. Let's assume that we have a mass attached to the end of a massless string, and this mass, there is a force acting on this mass, and the mass is rotating around around this fixed point. Now, in this case, the whole system we can treat as a rigid object. So we know that the forces acting on this is the tangential force, and this force, which in the simple example we assume to be perpendicular to this radial direction. So the tangential force will create a central acceleration, and this force, which is tangent to the trajectory of the object, will create the tangential acceleration. And the tangential acceleration multiplied by the mass of the object should be equal to the force acting on the object. Now we know that the tangential acceleration is related to the angular acceleration of this object. A tangential acceleration is the distance from the rotation axis. In this example, it will be r, multiplied by the angular acceleration. So force is equal to mass times the distance from the rotation axis multiplied by alpha. Now again, if we go back to this simple system, and if we multiply the torque in this example will be given by the force times this radial distance, which will be equal to m times r squared times alpha, because the force is already determined as mr alpha. So now we find the relation between the torque and the angular acceleration for a single point object. Now let's see what happens if we have more than one point object. So we can consider an arbitrary system. It is rotating around, let's say, some fixed point. This is the rotation axis. And for this system, we can divide it into very small parts. It can even be a collection of different point-like objects. We can, for each one, there will be feeling some torque. And we can use this relation for each one of those parts making the system. So the torque acting on each part will be its mass. It is distance from the rotation axis squared multiplied by alpha. Note that since if this is a rigid body, alpha, the angular acceleration of all the parts of the system are the same. So that's why I don't have alpha I. Alpha is the same for all the objects in the system. If we calculate the total torque acting on the system, the total torque acting on the system will be mi/ri squared multiplied by alpha. Since alpha is the same for all different parts of the system, we can take it out of this summation sign. So the total torque acting on the system will be equal to this number multiplied by alpha. That number, which is m1r1 squared plus m2r2 squared plus just the sum for each part, is usually denoted as I, and it is called the moment of inertia. So we see that for a rigid body, the total torque acting on the system is just the moment of inertia of the system multiplied by its angular acceleration. Now, when we look at the total torque acting on the system, the total torque, which is created by forces acting on each one of these parts, well, the forces acting on each one of these pieces making the system can be an external force or a force exerted by some other part of the system. So this part will be exerting a force on this part and hence creating a torque on this one and vice versa. But these internal forces, since they are on the same line, when we are calculating the torque, they will have the same lever arm, but just pointing in opposite direction. They will have the same lever arm, but they will be pointing in opposite direction. So in this sum, the internal torques will just cancel. So here in this sum, the only thing left is the external torque acting on the system. This is the torque created by the external forces acting on our system. And the total external torque will be equal to the moment of inertia of the systems for rotation around this fixed axis times alpha. Note that this equation is derived for systems that are rotating around the fixed axis. That is, an axis that is fixed in some inertial reference frame. So it will also be valid if this axis is moving at constant speed relative to some inertial reference frame, because in a different reference frame, that axis will also be fixed. It will be at rest. And also note that this expression is also valid if the torque, the external torque, is calculated relative to a rotation axis that has a fixed direction, but it is passing through the center of mass. In this case, the moment of inertia should be the moment of inertia for that axis. Now, this expression, the second line, is valid if the axis is passing through the center of mass, and if it's the direction of the axis is fixed, but if the center of mass is accelerating, then the axis might be accelerating. So this is valid at all times if the axis is fixed. This is valid when the axis might be accelerating, but it should be passing through the center of mass, and it should be have a fixed direction. Now, here, the moment of inertia over here plays the role of the mass in the case of the linear motion. The mass is an inertia resisting acceleration. Moment of inertia is an inertia resisting angular acceleration. It will be resisting rotations. And if you look at the definition of the moment of inertia, note that it's not proportional to just the mass. It also, for a given point mass, it is given by the mass times the distance from the rotation axis squared. So if the mass is further away from the center of mass, in that case, it will have a larger moment of inertia. So the moment of inertia of a given system depends also on the shape of the system, not just on its mass. So if the masses making our system are located further away from the central axis, rotation axis, then the system will have a larger moment of inertia. And note also that the torque over here, since it depends on the rotation axis, and if the rotation axis is different, the same force creates a different torque. The moment of inertia depends on the distances from the rotation axis. So if you take a different axis to calculate the moment of inertia for the same system will be different. Now, in general, you can use this expression to calculate the moment of inertia for simple systems. So as we will see in future videos, we can just convert this to an integral and evaluate the moment of inertia for sufficiently simple systems. But if the system is not sufficiently simple, another way of determining the moment of inertia is to measure it experimentally. So what you do is you just apply a known force at a given point. So you know the external torque. You measure the angular acceleration. The ratio of the torque to the angular acceleration will give us the moment of inertia of the system.